So, okay, let's start, huh? Okay, so you see this last lecture that we talked about this morphology of single yarn and that we talked about the yarn diameter. And in the there that we have seen in yarn diameter particularly how this yarn diameter is going to be calculated if we know certain values, or issue was that on what factors that the yarn diameter depends. So that there is a need that we have to develop a model which can address all the variables deciding yarn diameter. And we arrive to a this formula for yarn diameter, that d is equal to k1 plus k2 whole multiplied with t to the power q z to the power c, where that we saw that value k1, k2. K1 is a fiber dependent type of fiber. If you are using, how the yarn diameter will change, and that constant k2, that we found that it is a technology dependent. If I'm using different spinning system like a ring, rotor, air jet and all, so this value of K2 will take care of that. And of course, then we got some other coefficient, that is Q and C, corresponding to this type of fibers, type of technology. And there also that we realized, yes, if it is depending on type of fiber, then definitely the issue will be if I'm going to make a blended yarn, where that I'm using two different types of fibers in different proportion. So if two different type of fibers are there, then definitely we have to find out this different values of K1, and this will also vary the moment that the proportion of fibers in the yarn will also change. So for this also we have worked out and calculated this value. So overall that we reached to a conclusion, and we compare these results with the earlier models, and we found that the proposed model definitely give better results in comparison to earlier model. But we have again raised the issue. Still there are certain issues in this particular model have not been addressed, which will definitely decide this yarn diameter. Like suppose that I'm making yarn with different spinning tension, different speeds and all. So the spinning tension will change. And then the spinning tension will again change the yarn diameter. That issue, like suppose that I'm making yarn with different draft level, say ring frame. I'm making this yarn with the 20 draft or say 40 draft. And definitely the diameter of yarn with 40 draft will be lesser, because the drafting force in case of 40 is higher, and that will bring this fiber closer during drafting. And automatically this diameter of the yarn will reduce. So this we have talked. And at the same time, then in earlier lecture, we have also talked about this number of fiber in yarn cross section. There again, that we have proposed a new model which is addressing again a good number of parameters deciding this number of fiber in yarn cross section. Because earlier formula, whatever that we were using, has a limitations. And there that we talked this number of fiber yarn cross section will be packing density of the yarn multiplied with sec beta minus 1 divided by 2 pi f z square, where packing density of the yarn is known to me, helix angle beta is helix angle, and f is the cross-sectional area of the fiber, and Z in the twist. So it means it is indicating that yes, number of fiber in the cross section will depend on packing density of the yarn, helix angle of the fiber in the yarn, the twist in the yarn, and cross-sectional area or fineness of the fiber used. So these two models that we have, and then further that we arrived this reduction percentage that is equal to tangent square beta by 2. So different relationship. Now keeping that background in mind, now take a issue. Suppose I have a yarn cross section, which I'm showing on this slide. So this is a yarn cross section, real yarn cross section, how these fibers they look like in a yarn if I cut the cross section. How to cut the cross section and all that I will talk later. But at this moment, just if assume that I have uh, a cross section of the yarn is given to me. So what are the information this cross section is given to me, and how that these information I can use to explain the mechanics of yarn structure. So now this is suppose of fibers which I'm showing, but this one looks the actual cross section of the fiber, so how fibers they look like. So suppose I have a cross section of yarn. So what are the information I can get out of it? That first information I will get actual number of fiber in yarn cross section, because that we know that a number of the fiber will depend on type of fiber I'm using, amount of twist that I'm giving, packing density, and all these factors will decide this number of fiber in yarn cross section. So this is another information. Second information this cross section will give the total area of fiber in yarn cross section. If I calculate, say, this area of individual fiber, and then I sum up all these values, and then I will be in good position to calculate the total area occupied by the fiber in yarn cross section. So total area of fiber in yarn cross section, that another information I have. Then of course this is the center of gravity of a yarn cross section. So the center point, how that fibers are distributed, and this information I will use later once I will talk about radial packing density of the yarn at some stage. And then another information is packing density of fiber in the yarn. How packing density I can calculate? Suppose that I know the area occupied by the fiber in yarn cross section. So in that case, that I'm taking the area of individual fibers and summing them up. So that will give you the total area occupied by fibers in the yarn cross section, and then the cross sectional area of the yarn. So ratio of these two are giving me this packing density of the yarn. So it means these four information a cross section it can give. Okay. So now keeping that in mind, now let's talk a certain relationship which will decide this or explain the mechanics of yarn structure. Okay. So now if we say if SI star is the average area of fiber, because you see that here that you have seen the fibers, those are placed at different position of a radial position of yarn have different area. Because all fibers doesn't have the same area. Even though that the cross-sectional area of a fiber is fixed, but depending on their radial position in the yarn will decide the area of the fiber. Take a typical case. Suppose my fiber is straight and parallel to yarn axis, and I cut the cross section, and my cross sectional shape of the fiber is say circular. So the moment I cut the cross section, I will get the this is a circular cross section. But the same fiber, if it is inclined at angle say beta I, where I is the radial position of the fiber, so in that case the cross section of the fiber will not be circular. It will be elliptical. So it will form a elliptical shape. And now that the area in this case, that once we get the elliptical cross section, then this your minor axis of this ellipse will be equal to the diameter of the fiber. But major axis of the ellipse will depend on helix angle, that is beta I. But in general, the area of ellipse will always be more than the area of circle. So what does it mean? That the fibers placed at different position from yarn axis will have now different area. So for that, what we assumed here, that if Si is the average area of the fiber, so that we have say n number of fibers, we have calculated the area of individual fibers, and then we have calculated the average, so average area of fiber. So now total area of fiber in yarn cross section will be, if suppose I'm taking NE wherever that you see here, that you have to be a bit careful. I will use this terminology E and T. E wherever I'm writing, then it is experimental value, actual value. And if I will write T, here like that, here it is ST, so this is theoretical value. So that I will use this terminology everywhere. So now suppose Si star is the average area and N is the actual number of the fiber experimentally, this number of fiber in yarn cross section. So number of fiber multiplied with average area of the fiber is nothing. It is actual area of the fiber in yarn cross section. Okay. So now we know, the moment that I know number of fiber in cross section, if I know the average area of the fiber, individual fiber, then I'm in good position to calculate the total area of the fiber in the yarn. Now, same thing that with our earlier lecture, we have also found some other relationship. So, total area of the fiber yarn cross section can also be calculated by following equation as T, that is your T over rho. And that is your theoretical area of the fiber, where T is the yarn fineness and rho is the your density of the fiber, so specific density of fiber. So that is again, so it means now I'm getting this two areas. One is SE and another is ST. SE is experimentally calculated area or measured area and ST is the theoretically calculated area of fiber in cross section. Now let's see that what is the relationship, and we found that now here that you see two things that we have got two area, but now let's see a yarn. Now I'm assuming that these are my fibers and they are all straight and parallel in yarn. That is the assumption. And if S is the area of single fiber, so single fiber, which is straight and parallel, and if S is the area of single fiber. So we can say S is equal to small t over rho, where small t is this fineness of the fiber. So now I know the area of individual fiber. Once the fiber are straight and parallel to yarn axis. So I got the relationship. So in that case, what will happen? So total area of the firing yarn cross section, if S is my this fiber, area of individual fiber, once the yarn are straight and parallel, and NE is the actual number of fiber in yarn cross section. So then we can say that is ST is equal to S over NE. Okay, but in real yarn that we found that ST is not equal to S into NE. That we found because otherwise technically what is happening? That here I know the area of individual fiber, I know number of fiber in yarn cross section, I'm multiplying it and I'm getting the total area of the fiber. But in this case, what is my assumption? Once I'm calculating the number of fiber in yarn cross section, my assumption is my fibers are straight and parallel, which we have taken in this figure. So I'm going with this assumption. And on that basis that I'm calculating this ST. And that's why I found that this ST is not equal to SNE, which experimentally that we found. So that in general that we found that ST is greater than S into NE. Okay, so this is that we found once we calculated or measured the number of fiber after cutting the cross section and all. So we found always that ST is greater than this value. So now let's see. This I'm putting this value ST. What ST is nothing, T over rho. A small s is equal to small t over rho multiplied with any. This what is this value? Capital T over small t means the fineness of the yarn divided by fiber fineness is nothing. That is the number of fiber yarn cross section, because this is the formula earlier that we were using. But in this case, it is giving definitely number of fiber yarn cross section. Then I'm going with an assumption that my fibers are straight and parallel. So in that case, this I'm getting this any. So what we found, NT is, suppose I calculate this theoretical number of fiber in yarn cross section are always greater than any. Theoretically calculate and versus that experimentally which I cut the cross section. So if I define then one factor, any divided by NT, where NE is number of experimentally measured fiber and NT is theoretically calculated fiber in yarn cross section. This ratio NE over NT, I'm defining one coefficient, say Kn. So Kn, wherever I will use now further, Kn is nothing, it is the ratio of NE over NT experimentally, experimental area, this number of fiber and theoretical number of fiber. So this now Kn that we always find, it is lesser than 1 in actual. What is indicating? What is this Kn? And now we have to understand the significance of Kn. You see, if Kn is reaching to 1, what is indicating? It means that experimentally area of fiber are increasing in the yarn. And if this N is equal to NT, so that the situation is that my fibers are all straight and parallel. But normally in yarn that you have imparted a twist. And the moment that you have imparted a twist, then fibers will not be straight and parallel. They will follow a helical path. And the moment that fibers are following helical path and they are placed at different radial position, so their helix angle will be different. And once the helix angle will be different, then definitely the fibers are inclined from yarn axis. So the moment that the fibers are inclined and I'm cutting the fiber and cutting the cross section of the yarn, so number of fiber in the yarn will be lesser. And that is the reason that your NE is always this lesser than NT, or that we can say Kn will be this lesser than 1. But suppose I have 2 yarns and I know now this value of Kn, and here that you will understand the importance or significance of this factor Kn. Suppose 2 yarns, in one case my value of Kn is 0.9. Another case my value of Kn is 0.8. And now I will ask you which yarn is more aligned towards yarn axis. Yarn having Kn 0.9 or yarn having Kn value 0.8. Anybody can tell? Question is clear? Because I'm trying to see the significance of this factor Kn, how this information related to Kn can be exploited for our further knowledge about yarn. So I have given a situation, 2 yarns that I have, and I found in one yarn that the value of Kn is 0.9, another yarn that I have value Kn 0.8. What is indicating? Why one yarn Kn value is more? So what is indicating in comparison to other yarn? Anybody?
Sir, in Kn 0.9, the fibers are more straight and parallel.
Correct. You're absolutely right. So it means what has happened is, suppose that you as a spinner, you are making the yarn. And the moment that you measure the value of Kn, and your value of Kn is reducing, so it is indicating the fibers are more disorientated. They are not straight and parallel. So it means that what you will do, you will just optimize your spinning process, and so that you will try how I can increase the value of Kn. And if your after optimization, your value of Kn is increasing, then it means that you have optimized your parameter in a better way, and you are able to achieve more fiber straightness and parallelization. So you have understood the importance of Kn. So you use this information into practice also, and it is giving you very good information. So immediately that I will optimize my spinning process, blue room, carding, drop frame at different stages, where that I am noticing that my fiber straightness and parallelization is deteriorating. I will change my parameters accordingly so that I will try to improve the value of Kn. Okay? So Kn is clear, or anybody has any doubt at this stage? Any question up to this point?
No, sir.
Okay, so now let's and talk about another coefficient. Now, what happened? That you see, remember, in first case, what was my assumption? My assumption was my fibers are straight and parallel. But in a real yarn, there is a twist. So fibers are not perfectly straight and parallel. They are aligned. So take a question, the situation here. This is the cross, your yarn will look like. So that they are following a this helical configuration. So this is the situation. So it means that fibers are not straight and parallel to yarn axis, which is indicating here. This is my fiber. Take a typical fiber, which is parallel to yarn axis. But the same fiber, if it is inclined at angle beta from yarn axis, and the distance of this fiber from yarn axis is say Ri, so what is going to happen? That if the cross-sectional area of the fiber is S, so in this case, the fiber which is placed at this ith position, at the radial position in the yarn, so that my area will be say S star. And this area will be definitely more than this area. Because this cross section will not be circular, it will be elliptical. And this is my circular. So the area of ellipse will always be more. So it means the fiber which I'm using in the yarn, and now that if they are inclined due to this helical configuration, twisting and all, so that their area will change. Okay. So keeping that in mind, then now we'll go further. So in this case, what is going to happen? If suppose S is the area of individual fiber, and S dash is the area which is placed at say ith position. So S will always be lesser than S dash. And why? Because S dash is equal to S over cos beta I. As my value of beta I will increase, then what will happen? That this value is going to increase. And that's why this your S dash is lesser than S dash. So this will the value of S dash is depending on this beta I, cos beta I value. It is clear? Well, how that the area of the fiber will change once that the fiber is placed at a different radial position, and once that they have a different radial position, definitely there this helix angle is also going to be changed. So the helix angle is going to decide the area of individual fiber. And if individual fiber area is changing, so the total area will accordingly will also get changed. So now that this relationship we got, now we know from helical model that tangent beta is equal to 2 pi, 2 pi Riz, that we have already seen, where Z is a twist in the yarn. So On the basis that we can say SE, this is a area experimentally calculated, is S dash multiplied with NE, where S dash is the this area what we have calculated, and that is your NE. So now that we can say again that we found that ST is greater than SE. I will put this value. What is ST? ST that I'm defining SE over ST, where SE is experimentally calculated area, ST is the theoretically calculated area. And that I'm defining now another factor Ks. Okay. And which we found that this Ks is also lesser than 1. Okay. We have found this this Kn also that we found lesser than 1. Because if now this Ks, as it is this reaching towards 1, what is indicating? Again, it is indicating my number of fiber in yarn cross section are increasing. The moment my fibers are straight and parallel, it means it will give more number of fiber in the cross section. And now here that you have to be a bit careful. SE is depending on two factors now. One factor, number of fiber in the cross section, and another is the average area of individual fiber. This area of individual fiber. So two factors. The moment that fibers are inclined, then what will happen? Your NE will reduce because the fibers are inclined. But area of individual fiber is increasing. So total area, that is the SE, will depend on now how many fibers in the yarn cross section are there. At the same time, due to this inclination, how that area of individual fiber has been changed. So these two factors will work together to decide SE. And now here that you see whether that this if increase of SE will be due to increase in number of fiber in the yarn cross section, and at the same time that the increase in the area of individual fiber. But they are in contradiction. If area of individual fiber is increasing, means number of fiber in yarn cross section are reducing. So that you have to see that what resultant combination we get it, and on that basis that the value of SE that we get it, and that will decide now this ratio SE over ST, and which as I said the KS, so KS is always lesser than 1. So there again that I will try that if suppose the two yarns have two different KS value, and the yarn have a higher KS value is indicating my fibers are more straight and parallel. So this is again that if the moment I know the value of Ks, and so I'm in a good position to see how my fibers are placed in the yarn. Now here in this model again, one of the assumptions that we have taken, which is again not applicable in real yarn. Here that you see, okay, in the first model that we have seen, we have taken into consideration fiber are straight and parallel. Then we found no, in yarn fibers are not straight and parallel, they have helical configuration. So in second case, we have considered a helical configuration. But even though that we are saying why this KS value is lesser, one of the aspect that again that I'm missing into consideration, that is fiber migration. And now what is fiber migration? And this, of course, it is a separate chapter which I will take later. But for time being, that I will tell you what migration is. Take a consideration once that I'm making a yarn, I'm drafting the fibers, I'm twisting the yarn. During drafting and twisting, the fibers will have some tension. So they will be under tension. But once that yarn is formed, these fibers will try to come under minimum energy state. So they will relax. So the moment that the relaxation of fiber takes place after yarn production, they will change their path. So they will not follow their exact path, what path they occupied during yarn preparation. Because fibers are under tension, they will relax, so they will change the path. Now there are two situations. Either fiber will come towards yarn axis or it will go towards yarn surface. If a fiber is coming towards yarn axis, the area of that fiber is reducing. But as this fiber is reaching to yarn surface, the helix angle will be more, the area of fiber is increasing. So it means now that an important issue which we are missing in this model, that we have not taken into consideration this fiber migration. And this part that I will take later, and then accordingly we will make some correction factor once that we will discuss the fiber migration in the yarn at a later stage. But for time being, that yes, you keep this question in mind. This up to this stage, that the fiber migration has to be also taken into consideration. Then only I will be in a good position to say that we are talking about real yarn. Otherwise, in real yarn, that migration is always there. In this case, once that we have calculated the KS value, we have only considered that yarn is following helical model, which is not true in real yarn. This point is clear? That's KS. Or anybody has any doubt or a clarification? So any question? Before I just take some case studies, I will explain this value of Ks and Kn, and on that basis that we will explain different yarn properties. So you'll realize the significance. Yeah, please.
So can you please repeat why the theoretical value of number of fibers in cross section is greater than the experimental value?
In case of Ks, you are talking or general?
So
You see, this
generally,
is suppose that you have a parallel bundle of fiber and you cut the cross section. Then in that case, how many fibers? You will get actual number of fibers, whatever that you have. But if suppose the fibers are inclined, so number of fiber in yarn cross section will reduce the moment I will cut the cross section. And now that if the moment that fibers are inclined, then we said the area of individual fiber will increase. And Ks is depending on the area of the fiber, this area occupied by the fibers. So now two situations are happening. Due to this, the moment that we consider the twist in the yarn, my number of fiber in yarn cross section will reduce, but area of individual fiber will increase. And my total area SE in the yarn is depending on now this number of fibers as well as the area of individual fibers. So here that this if suppose my value of SE is increasing, so that we have to see that whether this number of fibers are dominating or increase in the area of fiber is dominating. So one of the factor will be dominating to say if my total area of the fiber is increasing. So it means the important issue is that we have to also consider the radial position of the fiber in the yarn. How fibers are placed from yarn axis. And that is going to decide both the things. If fibers are more inclined, number of fiber in the cross section will be lesser, but area of individual fiber will increase. The total area is depending on number of fiber as well as average area of the fiber in yarn cross section. It is clear or still doubt?
So increase in the number of fibers is dominating the decrease in area.
No, this situation will be that's something. The two different situations are going to be. You see, if suppose number of fiber in yarn cross section are increasing, then average area of the fiber in a yarn cross section will definitely reduce. And total area is this your area of average area of the fiber multiplied with the number of fiber in the cross section. So two different situations are there, and that you have to say which factor is dominating: increase in number or increase area of individual fiber, and that will vary from situation to situation. The total area will definitely depend. If suppose I may have a situation, because I will show you this the case study, and maybe that this point will be clear to you. Okay, let's take then again you raise this question here. That you see this is the table. Now here you see this what we did. This we made this yarn. We call it double roving feed system. Double roving feed system. What we are doing? It is normally ring spinning system, but instead of one roving, which normal case we do it, but in this special case that we have fed two rovings parallel to each other and draft them and making the yarn. So means two strands are getting drafted individually, and at the nip point they are getting converged, and we are making the yarn. So the difference is this two roving feed versus single roving feed. So here that we have also made this yarn single yarn, which I'm saying single yarn is nothing. That is where that I'm feeding one roving, and here in these three cases that we are feeding two parallel roving, and we are making the yarn. Now once that we are feeding two roving, then definitely their issue will be the what should be the distance between two rovings which I'm feeding. So we took this as a variable. So we used this 6 mm, 8 mm, and 10 mm. This from center to center of two rovings. That distance we kept, and then we wanted to see that whether that the distance between two rovings is playing any role or not. So that was the idea to study, and we took this roving distance as a variable. Okay. So what we did, we made this yarn, this on an average 30 NE, this 29.56, 29. So here in the three cases where that it is a two roving feed, and here single roving feed. Now that we have calculated the value of NT, NE, and KN, and of course here that ST, SE, and KS. Now you typically, what you are noticing? If I see this value of NE, this in case of sorry NT will definitely depend on what is T over small t. So this is yarn fineness divided by fiber fineness. So that I'm getting this value of NT, and any that we are getting this experimentally, that which we cut the cross section and measured it. Now here very interesting thing that you are noticing. Then in case of all double roving yarn with the roving distance 6 mm, 8 mm, and 10 mm, if we compare this now NE with the yarn where I fed a single roving, that you'll find this is more 168 number of fiber in the cross section. Here number of fiber in the cross section are lesser. Now another interesting phenomena that you are noticing, as my roving spacing is increasing, that here it is 6 mm, here it is 8 mm, and here it is 10 mm. As roving spacing is increasing, that my number of fiber, actual number of fiber in yarn cross section are reducing. And this you can correlate with this theta angle. Because as roving spacing is increasing, my this angle theta is also increasing. So here that you say in case of single yarn, my this angle theta is 18 degree. But in these yarns, it is more than 18 degree. So now suppose my fibers are inclined lesser, definitely it will give more number of fiber in yarn cross section. If my fibers are inclined more, they will give lesser number of fiber in yarn cross section. So that's why my any value is lesser, and then accordingly we have calculated the value of Kn. So Kn that you have noticed in case of yarn with the single roving, where that this twist, this theta was lesser, is giving you higher value of Kn in comparison to yarn where that angle theta was higher, is giving lesser value of Kn. And this is mainly due to this change in the value of Ne. This point clear? So why that vector effect, this Kn is lesser? Because in this case, that in double roving feed, that fed this two roving, they are apart at a distance, and so they are making more angle. So fibers are more inclined, and this your this number of fibers accordingly are reducing, so that Ne will reduce. So that is reducing also my value of Kn. Point taken? Or any doubt? Anybody has question at this stage before I go to KS? Any question?
Oh, no, sir.
Okay. Now that you see, if I say in a yarn, the value of Kn is increasing, means number of fiber in yarn cross section are increasing. What will happen to yarn strength? The strength of the yarn should be more where I have more number of fiber in cross section, or yarn strength will be more where I have less number of fiber in yarn cross section.
More number of fibers.
More number of fiber, higher the strength. Okay. So you keep this statement in mind, and I will answer once I will explain this case. Now take a case here. This ST is nothing, T over rho that we have calculated, and here that SE that we have calculated with the distance 6 mm, 8 mm, 10 mm, and here that SE of yarn with the single roving feed. Now, what is you are noticing? Again, that you notice this SE value of yarn with single roving feed is always more than this SE value in case of double roving feed. So this is one conclusion that we are drawing. Second conclusion, what we are doing, that the value of SE is in this here that you see, it is 36 to 242, and here 228. Now here that you see this SE is increasing up to 8 mm this distance roving feed, and after that it is reducing. But in general, then definitely SE is more in case of single roving feed. The same way that we have calculated the value of Ks. Ks is what? SE, this SE over ST. And there that we found that definitely SE is your, or sorry, factor Kn in case of single roving feed is more than this double roving feed. Okay. Now, on the basis of that, this we have calculated the packing density. Now, here that you see this statement what you gave now will be seen differently. Now, see the packing density. What is my packing density? Packing density is area of the fiber yarn cross section divided by area cross sectional area of the yarn. And this definitely this packing density will be maximum 1. So as that yarn is reaching towards 1 means yarn is more packed. And now if we say if the packing density of the yarn is increasing, your strength of the yarn will increase or reduce?
Strength will increase.
Increase. So this is the statement. Another statement you gave that this number of fiber yarn cross section is increasing, so that your strength will increase. You see, this both the statements are correct. But under some circumstances that you will find, in general, that you will find always, if you are increasing number of fiber yarn cross section, yarn strength should increase. If I'm increasing the packing density of the yarn, yarn strength should increase. But not all the time, because there are other structural aspects that they are influencing and not helping the same trend. For time being, I will give you one typical case. We'll see the packing density. Packing density that what you are noticing. Packing density of this your double roving feed yarn is higher than single roving feed yarn. Okay, but if you see the value of Kn, Kn value in case of single roving feed yarn is more. My fibers are more straight and parallel. Okay. So now if my fibers are more straight and parallel, my packing density should also be more. Here that we say my fibers are not straight and they are inclined, my packing density is higher. And if I take this issue from packing density point of view, because this is only one factor at this moment of structure I'm talking, because there are, as I said, there are other structural characteristics, those are also influencing my property. At this moment, I don't know. So I have only information related to packing density and area of fiber and number of fiber in cross section, so that our conclusion will be limited. Keeping that in mind, definitely what happened that here that packing density is more in case of double roving feed in comparison to single roving. And that is also true that double roving feed yarn strength is more than this single feed yarn. But number of fiber in the cross section in single feed yarn are more. So if I take this my conclusion on the basis of number of fiber in the cross section, and if number of fiber in the cross section are increasing, and then my strength of the yarn should increase, but it is not reflecting the same way. Here that my packing density is lesser, and here packing density is more. So now that we have to explain why it means the number of fibers are not helping to increase the packing density. Some other factor is influencing to decide the packing density of the yarn. Because these are my experimentally calculated value, I can't deny these values. So just experimentally we have done it. And we are finding that even though number of fiber in the cross section are lesser, packing density of double roving feed yarn is more. Here that is instead of having this number of fiber yarn cross section more, my packing density is lesser. So it means now in case of we have to understand how that we are making this yarn in case of double roving feed and single roving feed, and definitely there is some difference in making this yarn, and that's why this change that we are noticing. And what difference is, now take this double roving feed yarn. Double roving feed yarn, once you are feeding two rovings and they are converging, so it means two strands are coming one over the other. And these strands are putting a transfer force on the lower strand. and this lower strand after twisting it will come upward one. So it will put this your transverse force downward. So in that case, what happened? One additional phenomena has come into picture, which is pressing the fiber and increasing the packing density. So it is packing density increase is not only due to this fibers; those are coming closer, but we have put a additional your activity during twisting, converging of two strands, and which is absent in case of single roving feed. So what does that mean? It means that if once I'm explaining the your structural characteristics of the yarn, that we have to consider other influencing parameter also. Otherwise, the movement that I just simply say that I try to explain the structure on the basis of say packing density, then definitely from packing density point of view, you are in good position to explain this table that your this double room feed yarn has higher packing density, and that's why that strength of the yarn is more in comparison to single rowing feed. But you are failing this point here because you said it that higher the number of fiber in the cross section, more is the strength. And this is getting this neutralized by the additional phenomena which you have introduced while making the double roving feed yarn. This point taken?
Yes, sir.
So it means what the conclusion we are trying? That it is not simply that we have to see only one characteristics of yarn structure. We have to see other characteristics of the yarn structure. And at a later stage that I will explain, I will show you the case, even packing density of the yarn has increased and strength is reducing. Because there is a limit that up to certain limit, this packing density will increase, but there are some other changes are taking place. They are influencing the yarn properties. And this point I will stress every time in every lecture that don't see only one structural characteristics. You have to see the your structure of the yarn in totality. If you only see one characteristic of yarn, that maybe your conclusion may become wrong. Okay. So now here this is another case. This is in case of rotor spinning system versus ring spinning system. Now here that you see this, I have used a viscose fiber and polyester fiber. So this is my ring yarn, and here that I have this rotor yarn. So here that you see this is value of Kn. Kn in case of ring yarn is more in comparison to all yarn which we made on rotor spinning system. It is lesser. And on the basis of Kn, and that you know that ring yarn is stronger than this rotor yarn. So here that on the basis of Kn, yes, it is supporting that value of Kn is 0.96. So it is indicating that my fibers are more straight and parallel in comparison to rotor yarn. Rotor yarn that my value of Kn is lesser. So what we can say that definitely if I will find this helix angle of ring yarn versus rotor yarn, then helix angle in case of rotor yarn is going to be more in comparison to ring yarn, and that's why that it is giving lesser value of Kn. And practically we measured this helix angle. On an average we can say helix angle in case of ring yarn is around 12 to 13 degree, and in case of rotor yarn it is around 17 to 18 degree. And due to increase in this or more helix angle, this value of Kn is reducing. So what I will conclude here, now this two factors, this factor Kn and Ks, they are becoming a very important factor. They are giving a lot of internal this your characteristics of yarn, and which is helping me to explain the mechanics of yarn formation. And we are in good position if we understand this value Kn and Ks better. We are able to explain this yarn structure in better way. So that's why that it becomes important to understand this significance of factor Kn and Ks, and then we have to also understand how that we can use this information to explain this yarn property. Because here that you see in my entire course, that my approach will be, I will never say that the strength of the yarn has increased due to increase of draft or spindle speed or rotor speed or ruler setting and all. No, I will always say that these machine parameters are changing the structure of the fiber, structure of the yarn, and the change in structure is bringing the change in yarn properties. If my fiber orientation is different, my yarn properties are different. So the machine parameters which we change, and normally in literature, always the people they talk, because those have not studied the yarn structure, they will explain, oh, my increase of spindle speed is reducing the yarn strength. I will say that increase of spindle speed is disorienting my fiber. And due to disorientation, my strength is reducing. Okay? Any question? Anybody has any question? So, anybody has any doubt or anything? Please raise the question. Okay, if there's no question, so I will end it here. Okay, then thank you.
Thank you, sir.
Okay, bye. Have a nice day.